Okay, so there you go. So remember we were talking about NMR, nuclear magnetic resonance, and particularly so we had started with learning about the intensity variations. We started learning about the chemical shifts, and at the last we were trying to understand this part after doing away with this solvents effect of solvents. Finally we went back to the system of this ethanol and trying to understand the splitting patterns. So this is what the splitting patterns are called fine structure. This was I had already referred to in my last class, and it is coupling between the interact two interacting spins, two interacting nuclear spins that we are discussing here, which gives rise to this kind of splitting. And it is so if this is I1 I2 refers to uh, uh, the two uh, nuclear spin angular momenta, rather we should say in plural, and this is the interaction energy proportional to the scalar product of the spins. And this is how we arrived at first thing that resonance nucleus splits into because of the interaction of methyl protons with methylene protons. This splits into three, and the methylene proton splits into three because splits into four because of interaction with the CH3 uh, protons. We'll just think about this. So this was the thing that we learned: spin coupling constant, independent of they are. So few things that is it is the remember the Larmor frequencies of individual uh, nuclei was dependent, or of the same nuclei was dependent on like protons. If we are talking about protons, it was dependent on applied magnetic field. But the constant that we are talking about, that means the splitting that we will get will not change even if we change the applied magnetic field. So, and that's why we say that it is independent. So uh, under the high field or low field conditions, you're splitting the distance between these two splitted lines would be same. This is what it means. It is not going to change with the applied magnetic field. And then we started the discussion on, so there are two cases that we can clearly identify when we are talking about spins. There could be a X type system, that means two nuclei uh, interacting spins are having different chemical shift, very different from each other. So that's why in an alphabet A and X appear very far apart in terms of, so in a chemical shift scale, if they appear on very far apart, we will refer to them as A and X. If the two system interacting nuclear spins are having similar chemical shift value, then we can represent them an AB type system, representing taking analogy from the English alphabet, in which A and B are the closest neighbors. Okay, so that's how we start. And AX system is the first that we discussed in the last class, trying to discuss that one. And in that context, mhm. So individually we learned about this, how the spin applied magnetic field affects the spins, the two, when the field is off, the plus half minus half doesn't have any difference, they have same energy. But so this is something that we already know. And but when we have two such system A and X, then depending on whether what the orientation of the spin is, if both are upspin alpha A alpha X, if one is up, another in down. So x is down spin minus half. So alpha a bx. So these are four. So this you see, these are the four different combinations that we can have, and so the transitions possible can be correlated in the spin universe. So this is what we did in the last class already, so I'm not going to discuss it again. You can see the I think recordings have been shared for this one, so you can check with that. And the main thing was that whenever you have same spin alpha alpha x or beta a beta bx, then there is a rise. If the coupling happens, then there is increase. If the two spins are different, then there is always a decrease when this coupling is taken into account. Okay, so decrease in the two cases when one is plus half, another is minus half. This is the thing. And in that sense, so each starting from any position, you can start looking at it alpha. So starting from alpha a alpha x, you can change either x or either a, and you can get two transitions. Similarly, you can get two transitions in any way you consider for the V nucleus or A nucleus, sorry, A or X. And so these are the four lines that we get, which are having separations between them will be very the difference between them is given by this. That's the pictorially which we got from this understanding of these things. सो दिस पिक्चर्स आर इम्पोर्टेंट पिक्चर्स. अगर आप पिक्चर समझ गए हैं तो आप अपना कुछ भी लिख सकते हैं, बता सकते हैं. ठीक है, ठीक है. तो हाँ, सो this is how we correlated the things, spin spin coupling. So individually we can write for each one of them a and x, for x, for a. So we are so this we have already learned for a and for x, two nuclei, how this in applied magnetic field when they have their own electron cloud, so shielding and other things, how it will affect. And then so this energy was known to us, and then we added the second part. Additional thing that we introduced was this coupling hj ma mx, and that 1 by 4 term that you see, rise for the two things when either both spins are same, there is a rise due to spin spin coupling. In energy there is reduction in energy. So this is another way to represent the same diagram discussed as previously. Okay, so this is the system. So considering this way, you have this, so you can see there are four transitions possible, and this hj is much smaller as compared to mu a. So mu a, so what appears is that, so the two lines will appear at plus half hj and minus half hj for the given nucleus, for a nucleus, and similarly for x nucleus. And because of that, the appearance will be like this: x nucleus, two transitions, plus half hj minus half hj. So this is from the starting from the original isolated condition, x was here, now you are having plus half hj and minus half hj. So similarly here, this side also you are having for x. And so initially, if a nucleus was alone, there was no x interaction happening, then it was appearing in the here. And now because of this interaction, plus half hj and minus half on this line appears at minus half hj. So this is how we understand when the NMR spectrum, when the two spins interact and there is a coupling that happens, which the spin the coupled systems when we are talking about, This is how it affects the overall thing. So this already we have discussed. So this, the separation is half j plus minus half j plus half j. So separation is j. So this is how we understand this. We looking at this thing. So the way same way for mu a mu x both happened like this. And then so next we considered that what if the number of x increases, if it is ax2 ax3 ax4, how will this pattern change? So we got the two peaks. So now we consider so ax system and ax2 so the number of x nuclei appearing at far off position in the chemical shift scale is increased. Two, instead of one nucleus you have two nuclei and which interact with A. So in that case, because of the number of x has increased, the only the intensity for the, if you are looking at the signal for x, it will increase. It will same, the coupling will is going to happen with the uh, A nucleus for both the X nuclei, and each, so at the same position the splitting will occur and it will have higher intensity as shown here. Okay, so it's through this picture. So in the same way, if you go from AX2 to AX3, again you can think of rising in intensity at the two positions. So only the intensity is affected, the splitting is not affected. When we move looking at the X resonance in AX, AX2, AX3, AX4, the splitting is unaffected, pattern is unaffected for X, only the intensity rises. So it is still appears doublet with higher intensity. But if you at the same time we look at the resonance for A resonance, that will be significantly affected because 1A is now interacting with X, first nuclei number 1 X, nuclei number 2 of X, 3, 4 and so on. So depending on that, this is the kind of scheme that was that can be thought of, that the A nucleus alone, this is A alone, and then X first, X second, and this is how it will happen. So this is due to the coupling that happens. So it is split into with the same constant J. So this is how the separations happen. And now you can think of, so initially the A resonance was appearing here when it was alone. Now when there 1x, so this is the case of AX and this is the case of AX2. Okay, so what happens, you can think of it in this way. So this A resonance is split into two by interaction with by coupling with the X of first the first X nucleus, and then so we are getting two lines. Now each of these two lines will further split into two more lines like this, which we are doing. So you can see that two of them are coinciding at one position. So this is going to give you intense signal, high intensity, and in fact it will be double of the other two. So this is how you will, so that is what you are seeing over here. Okay, so this, the two things get added up, that they are appearing at the same position in the chemical shift scale, and so you have a increased intensity over here. So high intensity is apparent, quite apparent over here. So that's how. So AX is a doublet, but AX2, looking at the resonance of A, you will get a triplet. Okay, so each of the doublet line in the doublet is again split by the same amount by the second X. So this was the pattern. Two central transitions. Mm, okay, so splitting pattern. That's how we get the 1:2:1 ratio in this case, and you can extend this pattern and you will get what is called as a Pascal's triangle. So it will, so look at this picture, very nicely drawn one, with, if you are maintaining the scale, the length, the separation between this, you'll get exactly the kind of things here. 1:2:1, 1:1, 1, 3, 3, 1. So this is how it will look at. If you are not drawing the lines, and you can also put it like this. So you have one which is splits into two lines of equal intensity. Now the, if you have, so A and AX, AX2, AX3. So like this you can draw the pattern and go on. So what is, how do you make this triangle, Pascal triangle? It is very easy. So first one is very, you are looking at the signal of A, it splits into two of equal strength. Now the next splitting with the increasing number of X will happen in such a manner that the central one will be a sum of all these, the side ones. So 1 plus 1 gives you 2, and then you can also, so you have 1:2:1. Then if you are going to x3, 2 plus 1 3, 2 plus 1 3, so 1:3:1, and like that you can go on making it further. Okay, 3 plus 1 4, 3 plus 3 6, 3 plus, so this is how the splitting will happen. So this kind of scheme we are drawing for two nuclei, AX type, and for looking from the point of view of A resonance, the chemical shift position of A will be split into this fashion. Um, mm, mm, what else? Yeah, okay. So this is the Pascal's triangle, very useful one. It will help you solve many such problems in NetGet as well, if you just pay attention to it. And yeah, so what if so this was the patterns of coupling for yeah, we have already considered this Pascal triangle. um, so intensity is distributions of A resonance of an AXN type resonance, we can construct. So AX4 system again by this, considering the same set, 4 6 4 1. That's what, so it is a quintet. Quartet is this is quartet, 4 lines quartet, 3 lines triplet. This is quintet, इसको हम क्विंटेट कहते हैं. क्विंटिपल जैसे ट्रिपल होता, क्विंटिपल, क्विंटेट, ट्रिपलेट, इस तरह से. और ये क्वार्टेट था, ये ट्रिपलेट था, है ना. ऐसे आप देख रहे हैं, ट्रिपलेट, क्वार्टेट, क्विंटेट, और इंटेंसिटी रेशियो इस तरह से चेंज होती जा रही है. सो पैटर्न. अब दूसरा सवाल है कि अगर वो न्यूक्लियस, सो वो जो केस था वो हाफ न्यूक्लियस केस, हाफ स्पिन. इफ एम एस इज एस इज हाफ, सॉरी, द स्पिन क्वांटम नंबर विच गिव्स यू द मैग्नीट्यूड एस, द एस, उसकी बात हम कर रहे हैं, नॉट एम एस. सो एस इज, इफ एस इज हाफ स्पिन, हाफ न्यूक्लियाई मतलब जो फर्मियंस हैं. So all those nuclei which are behaving as fermions, and AX type interaction will give me this kind of splitting pattern. What if the nuclear spin is integral spin, I is equal to 1? It is not a spin half. Now they will behave as boson, I is equal to 1, and each of these lines will split into 3. So do you understand why it will split into 3, not 2? Because angular momentum का कितना orientation हो सकता है? If it is if I is equal to half, you can have so the spin angular momentum can have orientation which is given by mi, which is plus half or minus half. If I is equal to 1, the orientation will be given by plus 1, 0 and minus 1. So 3, 1, 2, 3. That's 3 different orientations. So this having the same magnitude of spin angular momentum, it can have 3 different orientation, and therefore such nuclei will give you when they interact, it will split into 3. The AX system that we are talking about, AX, X being X is I is equal to 1, X is having I is equal to 1, and so we are having this kind of situation where the first interaction splits into 3 because depending on the 3 different orientation of the spin angular momentum. Okay, so Z कंपोनेंट सबका अलग अलग है. तो याद है ना, हमने आपको S करके बताया था इलेक्ट्रॉन के लिए. ये न्यूक्लियाई में जो स्पिन है उसको I करके, जो हम स्पिन एंगुलर मोमेंटम का जो क्वांटम नंबर है I से डिनोट करते हैं, उसी का फिर ओरिएंटेशन है. सो दिस इज गिविंग यू मैग्नीट्यूड. So I, this is the quantum number that gives you. So don't forget the basic quantum number, which gives you the I is the quantum number that gives you the magnitude. Quantum number, magnitude of determines the magnitude of spin angular momentum, right? And the mi that I am writing is quantum number that gives you the Z component of the spin angular momentum. सो बेसिक आपको याद है तो कभी समझ के रखा हुआ है तो आपको कभी दिक्कत नहीं होगी कि वहां पे 2 क्यों स्प्लिट दिख रहा था, यहाँ पे 3 क्यों दिख रहा है, राइट? लेकिन वो नहीं है तो नहीं तो अगर वो नहीं आपको ध्यान में रहेगा तो फिर आप तो रट लोगे. हाँ, वैसा नहीं करना, समझ के करना है. ठीक है. सो 3 डिफरेंट ओरिएंटेशन. सो जब 0 हम लिख रहे हैं मतलब वो हॉरिजॉन्टली अलाइंड है. वैसे केस में आपका पूरा कंपोनेंट Z कंपोनेंट रहेगा ही नहीं. सो ये सब इमेजिनेशन अब आपके दिमाग में फ्लैश करना चाहिए. जैसे ही मैं कह रहा हूँ वैसे आपके दिमाग में फ्लैश करना चाहिए. इट शुड फ्लैश इन योर माइंड what I am saying, because you are not new to these things. You know these things, you are supposed to know because you have studied quantum mechanics, and in that we have discussed all these things. So because of that, so अलग अलग ओरिएंटेशन पे अगर होगा वही एंगुलर मोमेंटम वेक्टर, और उस अलग ओरिएंटेशन के साथ ए का इंटरेक्शन 3 पॉसिबिलिटी होगी, और इसीलिए 3 डिफरेंट आपको दिख रहा है स्प्लिटिंग पैटर्न में भी, corresponding to interaction energy, the alarm frequencies, how it is slightly affected by this coupling of spins, a X system. Now so we were here. अभी भी टाइम है, लेकिन आप लोग और दिन अगर 7 बजे ऑन द डॉट, सीधा 7 बजे आपको पहुंचना है, ऑनलाइन अपीयर हो जाना है, तो हम लोग विल बी एबल टू सेव लॉट ऑफ टाइम एंड it will be more, we will be able to utilize time more effective manner, because आप समझ रहे हैं हमें यूनिवर्सिटी भी जाना पड़ता है, तो इस ठीक है। और yes, I want to optimize your time so that you are able to give your time to perform your experiment project 2, so सब चीज़ बैलेंस करते हुए चलना है। so uh, so to in the need of to optimize that thing, we are doing it this way, that I am not forcing you to come to the classroom, actual physical classroom, but you can always come and discuss based on what we understand or we do not understand in the online classroom. If you follow the things, uh, you should try. I'll also give you a problem set to solve for NMR. Yeah, NMR and EPR together. Yeah, type of question banks. Yes, अभी सर्कुलेट कर सकते हैं, हाँ, जिसको करना है करेगा, नहीं करना है तो वैसे भी नहीं करेगा। ठीक है, ओके, सो आई विल गिव यू एनफ टाइम टू डू दैट। Yeah, so patterns of coupling, now you understand. Then yeah, the 3 protons of CH3 group. So now you apply why you are getting. So once we have theoretically understood what happens between A and X when they interact, AX2, AX3, now we apply those concepts to understanding this ethanol. एथेनॉल का जो ओरिजिनल स्पेक्ट्रम था, जहाँ से हमने एनएमआर शुरू किया था, वी आर कमिंग बैक टू दैट, trying to explain the things, right? So focus on CH3 group split into 3. CH3 splits into 3. So this is the triplet that you are observing clearly. So this dot, these 3, this is CH3 which is interacting with, so if this is my A, these 3 nuclei taken together is A, okay, and this is the AX consideration, and this is together as A, and this is X2, AX2 system. So this first nucleus of X, second nucleus of X, so AX2, and so hydrogen, the green one, indicating the interaction with the first uh, proton, which is CH2 methylene. So these two are CH2 protons. So the first proton of CH2, the second proton of CH2, and so AX2 type systems that we are considering here. And so all the 3 methyl groups are equivalent, they are affected equally. So initially, so first splitting 2, then because of the interaction with this, now second, each of these splitted line is further split into 2, each of them, because of this. So x1, x2, x2, second x. So this is how we can consider, and you are getting a triplet. Now is similar concept you apply to the other counterpart. This time you see the maroon part, the brown part that you see, this is CH2, this is taken as one unit, CH2, the methylene protons, CH2 protons, now they interact with So each of these methyl groups X1, X2, X3 system. So 1, 2, 3. So this is what we are considering. This is my A here. So in the AX type interactions that we are talking, we can think of this as these two nuclei together as A. उसका दोनों का signal एक ही जगह पे आ गया, but this will be initially like this. Isolated condition, a CH2 fragment should give me this kind of a single peak at this position, which will be further split in due to the interaction with the methyl protons, methyl proton number 1, proton number 2, proton number 3, and in this way you have a quartet, 4 lines of this pattern. You will see 1 is to 3 is to 3 is to 1. So clearly you can see how you are getting 1 is to 3. So if you compare the intensities, you actually the results that you get experimentally is verified by these theoretical considerations. OH resonance is not split because the so OH resonance is surprisingly, this is very interesting. OH resonance appears as a single line. वो भी तो वो जो प्रोटॉन है वो भी तो इंटरेक्ट कर सकता है ना, लेकिन उसमें प्रॉब्लम क्या है कि ये प्रॉब्लम या जो भी कहें, द बिहेवियर इज लाइक दिस that the OH proton is mobile. It is forming, it is polar bond, and the interaction of one molecule with the other, there is exchange of H. The OH is, it migrates rapidly from one molecule to another molecule, and so in this process the all average environment for it is there is no such interaction that can happen. Because of that, in all other cases a CH bond, H is fixed, it is not exchangeable, but OH bond, the proton is exchangeable, it can move, migrate uh, from one molecule to the other, and so we do not get any splitting pattern for this to happen, because the time scale of migration is faster than the data acquisition time for NMR. मतलब डेटा एक्विजिशन जो आप करते हैं वो स्लो है काफ़ी, अगर उस टाइम स्केल पे अगर हम कर पाते, सो जनरली ये सब चीज़ें भी आपको नोट करना पड़ेगा। ये मैं थोड़ा बाद में बताने वाला था कि मैंने सोचा था कि एनएमआर भी जब आप पूरी तरह से सीख लेंगे, then we can compare what take a molecule, NMR भी है, FTIR भी है, और तब हम कैसे उसको कोरिलेट करते हैं। कुछ चीज़ें हमें दिखती हैं NMR में, कुछ वही उस तरह का चीज़ और जो हम एक्सपेक्ट कर रहे हैं नहीं दिखती हैं, सॉरी FTIR में दिखती हैं, NMR में नहीं दिखती हैं। So some vital information we miss out sometimes in NMR, and we get that in FTIR because of the difference of the time scale की इसमें माइक्रो सेकेंड लेवल पे डेटा एक्विजिशन होता है, उसमें पिको सेकेंड 10⁻12, हाँ लगभग उस ऑर्डर का होता है। तो वो एक छोटा छोटा जो बहुत फास्ट जो कुछ हो रहा है उसको भी पकड़ सकते हैं उसमें, बट इसमें कई बार वो रोटेशन वाइब्रेशन का इफेक्ट कुछ नहीं आता है, क्योंकि उस एक साइकिल में जब 1000 टाइम्स दिस प्रोसेस, नहीं माइक्रो सेकेंड ना, हाँ 10⁻6 टाइम्स स्लोअर प्रोसेस हम डिस्कस कर रहे हैं। या सो दैट इज, सो टाइम स्केल समटाइम्स मैटर, टाइम स्केल ऑफ डेटा एक्विजिशन, ये बहुत इंपॉर्टेंट चीज़ है कि जो इवेंट हो रहा है और इस इवेंट को कैप्चर करने के लिए आपका इंस्ट्रूमेंटेशन सेटअप ही जो हो सकता है वो भी उतना फास्ट है कि नहीं उस प्रोसेस को कैप्चर करना, तो उस पर भी काफ़ी कुछ डिपेंड करता है। जैसे कि आपको फ्रेम पकड़ना है, फोटोज फ्रेम पर सेकेंड, एक फास्ट कैमरा होगा और हेलीकॉप्टर का ब्लेड को आप पिक्चर ले रहे हैं तो स्टैटिक, एकदम स्टैटिक दिखेगा, लेकिन अगर आपका नॉर्मल कैमरा है तो वही वो ब्लेड, अगर आप हेलीकॉप्टर का ब्लेड मूव कर रहा है फैन का, आपको वो मूव करता हुआ अजीब सा एक पैटर्न, मतलब पूरा स्मीयर्ड आउट पैटर्न दिखेगा, सेपरेटेड तीन पंखे नहीं दिखेंगे, ब्लेड्स नहीं दिखेंगे, इवन इफ इवन दे आर मूविंग। बट अगर फास्ट कैमरा फ्रेम पर सेकेंड जिसका ज़्यादा होगा रेट, एक्विजिशन टाइम कम है, तो उसमें आपको वो दिख जाता है। उस तरह से सोचिए। वैसी चीज़ यहाँ पे भी होती है मॉलिक्यूल के केसेस में। सो समटाइम्स थिंग्स occur. So here what we find that OH migration happens. H migrates from the OH, and because of that we are not able to find any coupling interaction, because this is limitation of the methodology rather than any other thing that we can see talk about. Then coupling constants, yeah, we can discuss the coupling constants maybe in the next class tomorrow. We can again, कल किसी का बैकलॉग एग्जाम नहीं है ना इसमें से? हाँ, तो ठीक है, कल इसको डिस्कस करते हैं. So we'll discuss the magnitudes of coupling cost. So I have given you a little bit of the recap of what we did last class and what we are going to do next. So magnitude of coupling constant, the equivalence, the chemical equivalent, magnetically equivalent nuclei, non-equivalent nuclei. These are the things that we should learn in the next class. Um, how these things are affected by the bond length, how the AX interaction. So the interaction AX we have talked about is A and X terminology we are using in when they are separated in terms of uh, chemical shift values A and X, but physically they can be closer, they can be far apart, depending on how many this separation of CC bond, if we are talking about say two protons of having two different environments, such that they appear at two chemical shift values very different from each other. But if they are separated by a large number of CC carbon-carbon bonds or less number of carbon-carbon, what is it going to affect the coupling constant, the interaction? Yes, and that we are going to consider in the next slide. How many bonds are there, and how what will be the effect on coupling constant. Maybe we can start this in tomorrow. So we have to tomorrow again you will so सुबह का टाइम सही है अगर हम सब कुछ देखें तो? ठीक है, नेटवर्क भी सही रहता है सबका, और आपके पास रिकॉर्डेड भी वीडियो रहेगा. ओके, एंड आपके पास जो बाकी टाइम है मैं हूँ डिपार्टमेंट में अवेलेबल, यू कैन डिस्कस. आप देखिए समझिए, देन यू कम टू मी, यू कैन डिस्कस एनी टाइम, नो प्रॉब्लम फॉर दैट. सो इसको मैं क्लोज करता हूँ रिकॉर्डिंग.